particular scaling symmetry that we get for heavy quarks inside n equals 4 always has this scaling exponent for the time coordinate as being 7. So the theory is invariant under x goes to lambda x and t goes to lambda to the 7 times t. And so this is called a Lifshitz geometry with critical exponent z equals 7. So if you take heavy quarks in n equals 4 theory and then ask what happens they back react, when they back react, it gives you a Lifshitz geometry with z equals 7. And it turns out that there are many different ways of looking at this smeared configuration of quarks. Some of them preserve supersymmetry, some of them don't preserve supersymmetry. What we have found with students and postdocs is that as a result of fair bit of technical work is that in all cases, whether we preserve supersymmetry or not, there seems to be a universal infrared description where you get this new scaling regime of z equals 7. Now this new scaling solution, this Lifshitz solution is interesting because these Lifshitz-like geometries or geometries which have this non-relativistic scaling symmetry have become quite interesting in recent years, where in the context of AdS CFT applies to condensed matter systems, where people have been looking for Fermi surfaces at strong coupling. So we have reason to believe, or we have the hope, that this infrared scaling geometry might shed light on something like a quark Fermi surface in the deep infrared. I will skip all this stuff. So the things that we are interested in now is that, in fact, we have some work in progress with these collaborators, that it appears, and we have strong arguments to believe, that this scaling solution, this flow towards this Lifshitz scaling regime, is in fact a universal feature and appears to be the case even when the flavors or quarks are massless. So in this D3, D7 system, if we consider the flavors to be massless flavors, then we can argue when the number of flavors is sufficiently large, using a kind of description of this system in which supergravity is perfectly valid, we can argue that the infrared regime of these systems is also described by this Lifshitz scaling regime. What we want to understand eventually is whether this Lifshitz regime has further instabilities. In particular, the kind of instabilities that we are looking for are sort of things that Alan was trying to mention, and these instabilities actually they correspond precisely to something like color flavor locking, a Higgs mechanism that can give rise to a phase that we may interpret as a color superconducting phase. So this is all work in progress, and since I'm out of time, I'm just going to leave this slide without getting too much into details. So thank you. Perhaps I can explain this if you have any detailed questions about this.
Question? Did you mention AdS work already?
Yeah, so I was out of time. So as I said, if you wanted to ask me the details, I can tell you. So what Alan is... Yeah. So what Alan is we're talking about is that if you look at what's happening from the perspective of these D7 grains, which you can, the Higgs runaway instability that I talked about, it can actually be viewed as some of these D3 grains, right? And so there are both D3s and D7s. You can view this as actually D3 grains coming and dissolving into the D7 grains and forming a bound state. Okay, and when they do that, there is a Higgsing that occurs. And in fact, if you look at the D3s dissolved inside the D7, if you look at it's like a defect inside the D7, and it's a codimension 4 defect. So it's like an instanton inside a D7 grain. Okay, so the instability that I was talking about corresponds to the fact that these instantons inside the D7 grain can have arbitrary scale sizes, and they can the scale size can run off to infinity. That's what Alan is talking about. What is interesting is if you can cook up a system where this instanton is formed, but its scale size stabilizes at some fixed value. Then this Higgs mechanism would not be a runaway instability; it would be stabilized. And then you would say this is a genuine stable Higgs phase and a color superconducting phase. Okay?
So
that's what we are trying to get at.
So
is
you
that
cook it, or you are working?
well, so the point is the way we think that it should work is that we think that it's very important that you should have the back reaction of the flavors. And I believe that was something that you did not have included completely in your analysis.
Oh, I see. Now, it was basically supergravity, so the
yes.
calculation was too complicated. I wanted it to linear.
Exactly. So the point is, the reason why this looks promising is because the infrared is now described not by a dirty supergravity solution, but by a Lifshitz solution.
Oh, I see. Okay,
right?
that's nice.
So now what you want to do is start asking the same questions that you asked, whether there is an stable instanton on the D7 ring, but then do this in the Lifshitz background.
Oh, I see. Yeah,
And
we did it in OA. That was not available at the time.
right. So we don't know as yet what's going to happen.
Oh, I see. Okay.
But we think that even if there is an instability in the Lifshitz background, we can cook it up so that we can stabilize it.
I see.
But that remains to be seen.
Because I talked to some of the people in Stony Brook, like they doing like color spot and sensitivity. They make a big deal, like, because this is still a scalar condensate.
Yes.
Right? And then they still make a big deal, like this is going to be different from like fermion by linear.
Yeah. So you don't. So actually that.
Is there something getting improved over the years? Like,
No, but so I think that argument, I mean that objection still stands. But the point is, when you go to strong coupling, you don't know what the condensate is due to. You don't know whether it's due to scalars or whether it's due to fermions. There's just one operator, and it's got both composite fermions in it and it's got scalars in it. And what you might want to look for is signals of some Fermi surface. Maybe that's the kind of question that one should be asking. So that's why strong coupling, that's a question that's almost meaningless in a system that has both fermions and scalars. It's hard to disentangle them. In fact, unless there is some selection rule that tells us that differentiates the fermion condensates from the scalar ones, there's no way to tell them apart. In fact, there should be both of them.
I think for this problem, it's got, if this is strongly coupled, it can be the Bose-Einstein condensation type of. So this, I think, this is not a big problem.
The what? What?
I mean, kind of BEC. So I mean, two diaphragm.
Yeah.
I mean,
It could be. So no, but it could, we don't know whether it's a.
Okay,
we don't know whether.
Is that for color superconducting phase, this scalar is color.
Yes. In fact, the system exhibits. So you won't see a color. You see. So that's in a fixed gauge.
Yeah.
The fact that the condensate is colored is only in a fixed gauge.
Mm-hmm.
You can only describe order parameters that are gauge invariant if you want to be careful,
okay.
right?
This
So
is-
there's some gauge.
yeah.
So what's really important is that you have some description of your theory in which there is a Higgs mechanism occurring. Color superconductivity, the key point is that there is a Higgsing of the gauge group, and that occurs here. In this setup, there's a Higgsing of the gauge group. What condensate leads to the Higgsing is just a composite gauge invariant operator that leads to the Higgsing. You can't tell from here whether it's a fermion bilinear or something else, but the fact that there is a Higgsing, that's the only thing you can tell from a gauge invariant framework and at strong coupling. So all of this is at strong coupling, that's the whole point. So
Prem, your NF and NC are of similar order now, is it?
they are of similar order in N, but actually NF is NF over NC is something like 1 over square root lambda.
Oh, I see. So it's still okay.
But it's still, but in terms of large N scaling, NF and N are comparable. And in order to make this work, actually, in order for a supergravity, I mean, this is much more subtle, and I didn't want to get into the details because this is not the right place. The point is that normally there is a problem in taking the Veneziano limit because of this fact that the open string coupling on the D grains becomes large, and then you can no longer trust what you're doing. However, there is this framework which has been developed by Carlos Nunes and all his collaborators in Santiago, which basically corresponds to looking at smeared flavor brains.
Oh, I see. Okay.
So when you smear the system, there are two things that happen. You sort of get rid of this problem of the effective open string coupling being large. Okay, so you get rid of the problem. The other thing that you find is that because you smear them, all the flavor brains, the flavor symmetry is abelionized now. And because it's abelionized, you need only the abelian dBi action to work with. Okay, so you can back react the abelian dBi action on supergravity, and that's how they construct these solutions. What's also interesting is that these frameworks preserve n=1 supersymmetry. And n=1 supersymmetry is different from n=2. There may not be runaway directions in n=1.
So you took the geometry from by Carlos and Benich.
Yeah, so there is. So we haven't constructed the full interpolating geometry.
Okay.
But what we know is that the deep IR in their framework will always be described by this Lifshitz, which was found in the heavy quark unit. So
we didn't have Carlos as our name, but
yes.
to grab it.
Okay. So
Any more questions? No, let's thanks again.
Okay.
It's 3 wonderful lectures.
Thank you.